Okay, so I have a question for you. How do we actually measure the specific humidity of the air just surrounding us? Like, what's the best way to do it? Now, I could conceivably, take some air and start like cryogenically freezing it to the point where all the water is going to condense. That's one way to do it, and then measure that in a scale. That's not the easiest thing to do. And so what we're going to do here is we're going to invent this object. It's called an adiabatic saturator. It's right here. We're going to use this to figure out how some of the values we have can help us define this. There we go. Pen was being weird for a second there. So using this adiabatic saturator, I would hopefully be able to find what my specific humidity is for my regular room air. And how would I do that? Well, I would do two things. One, I would add water at a temperature such that the air passing through my saturator leaves being perfectly saturated. It's carrying 100% as much water as it can possibly hold. And using this temperature right here, I can actually figure out what my specific humidity is of the air entering. Now, how would this work? Well, let's walk through conservation of mass and conservation of energy and see how we could figure this out. So first off, conservation of mass for my air. Now, the air entering, the air exiting is the same. It doesn't change, so we're just going to get rid of the subscripts and call it just mass flow rate of air. For the water, it does change. So I have some water entering with my air initially. I have some water exiting with my air at the end, and there's going to be some water that's evaporating right here. So there is a difference between these. Now, what we want to do then is to finally bring in specific humidity because this is what we're trying to calculate. How do we do that? Well, we just get rid of the mass flow rate of water entirely. We say, okay, I'm not going to worry about you because the air is carrying you. And so if I know the mass flow rate of air and I know my specific humidity, I can calculate it. Like, Dr. Kidd, we don't know that. You're right. Don't worry. We'll get to a point where we can just solve for it. Okay, so with this, I can figure out, well, the amount of water that is evaporating is equal to the difference in my specific humidity times the mass flow rate in air. So at the end, I'll have a higher specific humidity, and so it's going to be carrying more water out. That's from the evaporation. Okay, now let's look at energy balance. So once again, we're just focusing on the air entering and the water that's evaporating here, as well as the air exiting. Like, what about the water that's entering? The water enters as part of the air, so it's already taken into account right here. Okay, so first thing we're going to do is we already have an equation for the mass flow rate of evaporated water. And so we're going to plug that in. That goes right here. When we do that, what we see then is that the mass flow rate of air is actually in every single term. And I can cancel them. And so I get this. The enthalpy at the end is equal to the enthalpy at the beginning plus the extra enthalpy from the evaporated water. Okay, we still have a problem. You're like, but I can't calculate this yet. You actually can. Like, this is all able to be calculated now. This is not terrible. So why is it not terrible? Well, let's see. First off, remember that this enthalpy right here and here, this is for air. And so we can put that in terms of specific heat. So let's do that. So I have my specific heat for the air here at the beginning and the end. You're like, but what about the water? Yes, we did have to take that into account because when we said specific heat here, we're kind of separating the air and the water. And so this right here is me taking into account the enthalpy of the water vapor, both at the beginning and the end. Okay, so looking at this, you're like, well, can I calculate my specific humidity at the beginning yet? Can I finally solve for omega 1? And the answer is actually yes. Now, why is that a yes? Well, I'll go through these terms and see what we don't know. So from our saturator, we would already know what T2 was. So that term's taken care of. From just measuring the room temperature air, I would know its temperature. So that term's taken care of. The saturated vapor enthalpy for the water that's entering, well, that's from the tables. The enthalpy of a saturated liquid at my final temperature, that's also from the tables. And then enthalpy of a saturated vapor at my final temperature is also from the tables. Okay, so like, yes, we know everything except for a specific humidity at the end and the beginning. And the thing is, we actually know this too. Why? Because we already had a calculation for the specific humidity when we have a completely saturated, some completely saturated air. And here it is. So this is my specific humidity at the end. It's a function of the partial pressure of the water vapor at that final temperature and my initial pressure. And so if I know that, I know everything, and I can finally solve for my specific humidity at the beginning. Whew. So there's a lot of steps here, but in the end we get two equations which aren't that terrible, and most of this stuff is coming from the tables. Like, that's all from the tables. This is from this equation right here. And I just have to have two temperatures. Now, the thing is, this adiabatic saturator, it's not realistic. It's not realistic at all. We don't use them to measure that temperature of the, saturated air. So you're like, well, how do we do this? How am I going to figure out that T2 so I can actually use this whole method? Why did you show us that? Well, those equations are important, but how we measure that second temperature, we don't use an adiabatic saturator to do it. Instead, what we do is we use some cotton. I'm not even kidding here. You can take a thermometer, you take some cotton, a paper towel, you get it wet, you make sure that it stays wet because it's going to dry out as it water vaporizes, and you just blow air over it. What you'll see is that the temperature in the room might be up here, but the temperature you're measuring when you have that water blowing over it is going to be much lower. This is what's called the wet bulb temperature, and that's equal to T2 in our previous equation. So this is what we use to calculate it. As a note, if you don't have some wet cotton or paper towel on your thermometer, it's called the dry bulb temperature. Why? Because the bulb, it's talking about that shape at the bottom here, is dry. Who would have guessed? So this is really, really close to our adiabatic saturation temperature. It's good enough to use for calculating all we need. So let's try it out. Here's an example. So we have air. It has a dry bulb temperature of 75 degrees Fahrenheit. Remember, that's just the temperature of a regular thermometer. And a wet bulb temperature of 60 degrees Fahrenheit. So this is me taking something moist, putting it around the end and blowing air over it. It gets cooler. As a note, this is also how you can keep cool on hot days. If you get your shirt wet and air is blowing over it, you'll feel much cooler. Why? Because the air is, you're feeling the wet bulb temperature, not the dry bulb temperature. Okay, we're assuming this is the pressure of our air in the room, and we have a constant specific heat of this for the air. Everything else we have to get from the tables. So it says calculate that specific humidity. Let's get to it. First off, we're going to grab some data. So this is all the stuff I have to get from the tables. First off, what is my saturation pressure at my wet bulb temperature? This I need to get my final specific humidity. This is the specific, so I can get the specific humidity of a completely saturated air for whatever this room is. Everything else is so I can get my specific humidity of the actual air. So if you see a 2, that's going with the wet bulb temperature. If you see a 1, that's going with the dry bulb temperature. The 2 is wet bulb, 1 is dry bulb. That's going to go through this entire problem. Now, we have all of our information, so let's go ahead and calculate the specific humidity for that wet bulb case. So I have everything I need here. I have my pressure already given. It was 13.8 psi. I have this partial pressure, which is the completely saturated, case, which is going to be 0.2564 psi. And I find out in the end that I have about 0.01177 pound mass of H2O per pound mass of dry air if I am completely saturated. If I'm completely saturated. So if I'm not completely saturated, it's going to be less than this. So omega 1, when we calculate it, that's the specific humidity of the room I'm actually in, it's going to be less than this value. So let's just plug into our equation. Here it is. As a note, if you look at T2 versus T1, what you'll see is that T2 is lower. So this term right here will be negative. And so I have a positive term plus a negative term. That's why the specific humidity is going to be less. It's always going to be less here. So I plug that in, and I get a specific humidity of 0.00833 pound mass of water per pound mass of dry air. And that's just me plugging in everything I've got right here. All of that went in. Okay, so hopefully this helps you. This is just one way we can tell how much water is in the air we're currently experiencing. Hopefully you now understand what the wet bulb temperature is and how it's different from a dry bulb temperature. And don't worry, this isn't something that just disappears. We actually really need these values as we go to our psychrometric charts next. Have a good one. See you later. Bye-bye.